Welcome to this explainer. You know, if you've ever looked at a soaring skyscraper, a perfectly balanced logo, or even a sprawling 3D digital landscape and thought, how do they guarantee that whole thing won't just fall apart? Well, you're in the right place. Today, we're unpacking the literal blueprints of reality, demystifying how visual reasoning and rigorous logic actually build our modern world. Let's get into it. Here's our roadmap for today. We'll be covering where geometry meets visual reasoning, exploring logical geometric proofs, diving into advanced Cartesian trigonometry, and finally, looking at real-world math applications. Okay, we're going to kick things off with a pretty powerful guiding thought. Euclidean geometry is where logic meets visual reasoning. I absolutely love this concept from our sources because it completely shifts the paradigm. We aren't just passively identifying shapes anymore, right? We're actively engaging in methodical, unshakable reasoning. We're literally building arguments out of lines and angles. Section 1. Geometry meets visual reasoning, the foundation of shapes. So, to build anything, whether you're an architect designing a massive physical building or a graphic designer creating perfectly proportional digital art, you have to start with precise properties. Take a look at congruency versus similarity. Congruency means shapes matching exactly in both size and shape. Think of them as absolute, perfect clones. Similarity, on the other hand, means shapes matching in shape but differing in size, kind of like a scale model of a building compared to the real thing. Now, to actually prove these relationships, we use specific classification rules. Think of these as the DNA of geometric logic. For congruency, we rely on rules like side-side-side or side-angle-side. And hey, we aren't just memorizing alphabet soup here. These are highly powerful foundational tools used to logically deduce structural relationships. They're the undeniable laws that let an engineer say, yes, for sure, these two support beams are going to behave exactly the same way under pressure. Moving on to Section 2, exploring logical geometric proofs, the power of deduction. This brilliantly illustrates the mechanics of one of the most elegant concepts out there, the midpoint theorem. It's a three-step process. Step 1, you draw a line joining the midpoints of two sides of a triangle. Step 2, through strict logical geometry, you deduce that this newly drawn line is strictly parallel to the third side. And Step 3, you prove that the line is exactly half the length of that third side. It just perfectly shows how logical deduction unrolls step by step. Engineers and architects use these exact properties, from simple triangles to complex quadrilaterals like parallelograms and rhombi, to ensure structural integrity. Because, you don't guess if a roof will hold, you prove it. Section 3. Advanced Cartesian trigonometry, beyond the right angle. All right, expanding our architect's toolkit even further, we're shifting our focus from basic flat shapes into a much wider 360-degree spatial realm. The crucial takeaway here is that we've broken out of the confines of simple right-angled triangles. By redefining sine, cosine, and tangent using x and y coordinates alongside a radius within the Cartesian plane, we can mathematically map absolutely any angle. We're no longer limited to triangles drawn on a flat sheet of paper. We are navigating a fully continuous mathematical space. Now, because we're working in 360 degrees across 4 quadrants, we need a really reliable system to keep track of our values. To accurately determine the positive or negative signs of these ratios across the Cartesian plane, we use the highly efficient cast diagram. Notice how in quadrant 1 at the top right, all ratios, sine, cosine, and tangent, are positive. Move over to the top left, quadrant 2, and only sine is positive. Down to the bottom left, quadrant 3, it's tangent. And finally, the bottom right, quadrant 4, belongs to cosine. It is just a brilliant, quick reference visualization that lets mathematicians and programmers instantly orient themselves. Section 4. Real-world math applications, bringing it all together. So why does all this matter? Well, by synthesizing Euclidean proofs with Cartesian spatial coordinates, professionals can solve incredibly complex two-dimensional problems. You use these exact principles for calculating precise angles of elevation and depression, which is absolutely crucial if you're plotting the trajectory of a bridge or even calculating the line of sight for a movie camera. You use them for determining accurate geographic bearings. This math is literally the backbone of surveying, structural engineering, and architecture. And honestly, it's the exact same math used in game development to program 3D virtual spaces. When a character in your favorite video game throws an object, the game engine is running these exact trigonometric calculations in milliseconds to figure out exactly where it lands. Crazy, right? But here's the thing. Mastering this isn't just about memorizing formulas. It requires a very specific mindset. Our sources highlight the art of problem solving, or AOPS, which is a method designed by former math Olympians. It utilizes a really cool problem-first approach. Embracing this mentality actually prepares you for advanced sciences by forcing you to actively deploy math as a tool rather than just passively receiving it. It pushes you to build the logical argument from the ground up, developing higher-level reasoning that goes way, way beyond a standard textbook. The absolute best way to grasp these sophisticated principles is to just jump into an interactive geometry environment and start visualizing these solutions yourself. You really need to be able to construct and manipulate geometric shapes on the fly, visualize abstract logical proofs as they transform, and test complex hypotheses in real time. Platforms like the National Library of Virtual Manipulatives exist precisely for this reason. When you actually drag the vertices of a parallelogram and see the angles automatically adjust while perfectly maintaining their underlying logical rules, the abstract suddenly becomes incredibly concrete. I'm going to leave you with a provocative thought. If you were tasked with building tomorrow's physical structures or designing the next great digital universe, how would you use these interactive logical tools to construct your reality? Whether it's the congruency rules holding up a skyscraper or Cartesian trigonometry rendering a massive video game world, this knowledge is quite literally power. I hope this explainer has inspired you to see geometry and trigonometry not just as math, but as the very blueprints of our world. Keep exploring, keep questioning, and keep building.